paper. So we can clearly say that since it is appearing bright, we can confidently say this is a blood product. So this image I downloaded from the RSNA review article. So this is showing some of some various structures such as the corticomedullary junction, the presence of deoxyhemoglobin, one of the cortical vein which is appearing bright. Calcification you can see in the choroid plexus, which is appearing dark. There are some bright microbleeds which are appearing in the thalamus, and also like we can see presence of myelin in the optic radiation. So with that, coming to the data acquisition part. So we use 3D spoiled gradient echo with multiple echoes, basically multiple Ts to compute the QSM. So we all know this is a very basic sequence, SPGR. We know that SPGR kills the transverse magnetization by using a RF or gradient spoiling method, so that we can generate either T1 or T2 star weighted image. So this is the signal equation for the SPGR sequence. So just ignore this K of X part for now. This is the proton density component, and the sin alpha here, this is the initial transverse magnetization induced by the flip angle, and this particular portion 1 minus e to the power minus tr by t1. So this is actually it tells us the recovery of longitudinal magnetization between the excitation pulses. Coming to the denominator, again, like this entire component actually tells us or represents the residual longitudinal magnetization after each RF pulse. So we can, as a fraction, as a whole, we can say that it is basically, this is a ratio of steady state magnetization, which is balancing between the recovery. We can say that recovery as well as the between recovery and residual magnetization. So and finally, we all are very familiar with this component. This is again like which is the exponential decay of T2 star with respect to the echo time. So why it is important to know all these signal equation is that if we change our parameters such as flip angle T or T, our signal actually changes. And for SWI contrast, we know that it is very important to balance the contrast so that, for example, CSF is not too bright or CSF is not too dark, so that we can see the pathology. Maybe for like first year and second year damage students, you can capture this equation so that you can use Python or Excel to plot the signal, and you can experiment and observe the signal variation by changing all these parameters. So you can use either Phantom or volunteers to do that. So we know that the gradient echo sequence there is no refocusing pulse here. Instead, we use a gradient magnetic field to rephase the spin. Particularly, we use a readout, or we can say that frequency encoding gradient for this purpose. So usually this has a negative lobe and a positive lobe. Whenever we apply this, the frequency of spins changes actually. So if you look at the K space, it has frequency and position information. So KX, this KX actually represents the position in K space, and this particular portion, right? If you don't apply the gradient, so the position of the KX will be 0, right? So this will be 0, and the moment if we apply the negative lobe, the position of KX actually moves from 0 to negative portion, 0 to negative, whenever we apply the negative lobe. And if we apply the positive lobe, it moves from negative to 0 first, and then from 0 to positive later. So this is how usually we use the frequency or readout gradient to define our KX component in the K space. So yeah, so whenever the gradient is applied, the precision frequency actually changes, and we can actually the frequency variation actually translates into different kx values. So we can say that simply we can say that this kx is a spatial frequency, we can say. So how do we calculate the kx? Kx value over time. So this kx over time, we can use this equation for that actually. So and also like if you see this diagram, we can see that t act by 2 is the time of application of our first lobe, which is the negative lobe of the gradient, and t act is the time for the second lobe. During this time only, actually, like we collect the data, meaning like we turn on our receiver and we turn on our ADC to collect the data during the t act period. So let's see the equation. What is happening here when we apply the first lobe? So look at this first lobe. So uh, when we apply the first lobe, the gx is our gradient strength. We can say that, for example, 2 millitesla per meter. So that gx is the gradient strength. So when we apply the first lobe of gradient strength gx, what happens is that the spins will dephase, and the kx actually moves from 0 to minus gamma by 2 pi gx of t. So the t actually like I'm replacing the t with t act by 2 because during the dephasing lobe application, this is our time. Next, again, like after this moment, we apply the rephasing lobe of the gradient. So what happens is that like the second lobe, again, the gradient strength is gx, kx or kx moves to the positive value from negative. So t is the total time. So we can get TAC by subtracting the TAC by 2 from the actual T. So I just replace the T with the T minus TAC by 2. So we will get the KX information of the rephasing lobe also. So now let's do the integration. Basically, integration means like adding up all these values. So if we add all these things, we can find the value of KX. So once we get the KX, so we can, once we get the kx, we can calculate the phase also. We can calculate the phase over position x over time. So the phase information. So let me. So the phase information is the input to calculate the QSM map. So we have the phase information right now. So we got the information from this all this by calculating the equations with respect to the echo time. Now, what happens to the phase if there is flow? Let's see that. For example, we have two tissues here. One is stationary tissue and other one is flowing blood tissue with flowing blood. So if we apply our gradient, what happens is that like phase will change, and the change in phase we can represent as delta phi. So we can represent this by the change in phase can be represented by delta phi. So for stationary spins, there are some equations actually. Like for stationary spins, the delta phi is proportional to time, and for flowing spins, the delta phi is proportional to t square. So this is again is a hypothetical example shown by Dr. Michael Lipton in his textbook called Totally Accessible MRI. This is to understand how the flow and flow compensation works in MR. So let's see that, like, for example, for stationary tissue, what happens? So for single unit of time, or time t equal to 1, we have phase shift 1. How do we get this? 1 into 1. Our time is 1, and the phase shift will be 1. 1 into 1 will be 1. So the phase shift will be delta phi. And the second lobe, for 2 unit of time, the phase shift will be like, we have 2 units of time. So 2 into 1 will be 2. So the difference between 1 and 2 is 1. So our phase shift will be delta 1. So if we add up, so what we get is that, like, for stationary spins, minus 1, the first one will be minus 1. Why minus 1 is that, like, we are starting the gradient with a negative lobe. So that is why I gave negative sign to the first phase difference, and second one is a positive lobe. So we can add this up to calculate the next phase shift. So minus 1 plus 1 equal to 0. So we don't have any phase shift, and we won't face any kind of flow artifact here. For flowing spins, so let's calculate the same scenario for single unit of time. Here the phase shift will be t square. 1 unit of time, it will be 1 square. So there won't be any change. 1 square will be 1. And for 2 units of time, so here the time is 2. So 2 square will be 4. So we can calculate the phase shift. The difference between 1 and uh, 4 is 3. So our total phase shift will be delta 3. So if we again, what is the net phase shift? We can calculate that again. So because it is negative lobe, the first one will be -1. Then again, positive lobe, we got the +3. So if we add up these things, we got a like positive value, which is 2, which tells us there is some net phase shift, and we are going to face a lot of artifacts here. So ideal situation is that like the total or net phase shift should be 0. Any value between like other than 0 will create artifacts. So again, so how do we compensate this? So we need to eliminate all these flow related artifacts and phase variations. So to overcome this issue, we use we design our gradient in such a way that will eliminate all the flow related artifacts. So for this purpose, we use a specific type of gradients called flow compensation gradients. So we need to keep in mind that our from the previous equation that for flowing spins, the delta phi is proportional to t square. So again, we'll do the math here previously, like from the previous example. So we have 3 lobes, one positive lobe, one negative lobe, but with higher amplitude of the gradient, and again like one positive lobe. So what happens like if we apply 1 unit of gradient length for 1 unit of time? So here t square 1 square equal to 1. So we got a phase value of 1. This is positive, so we can keep it as it is. And if we apply 2 units of gradient for 2 units of time, so look at this example. So 2 units of time means it is t square. Like we need to do 2 square, which is 4. We got a phase value of 4. So there is one peculiarity here actually. So the gradient strength is negative, and also this is twice as compared to the previous lobe. So we got a phase value of 4, and the difference between like 1 and 4 is 3. So we got a delta phase variation of 3. Because it is twice the amplitude, we need to multiply this with 2. So 3 into 2 will be 6. And this is negative, so we can give the negative sign to this particular phase value. So our total delta phi will be for this particular thing will be -6. Again, we come to the third lobe, which is again like similar to the first lobe, positive one. So our time is 3. So 3 square will be 9, and the difference between the previous phase shift, which is the 4 and 9 will be 5. The difference between previous phase value 4 and current phase value 4 is 5. So our total phase variation or the delta phase will be 5. Here it is positive because we are using the positive. So what happens like if we add up all these things? So we got like 1, -6, and 5. So if we add all these things, our net phase shift will be 0. So wherever there is flow, if we apply this kind of gradient magnetic field, we won't get any phase errors or high velocity signal loss. We won't get anything. So because our net phase value is 0. So this is again like that was a hypothetical example to understand the concept, but how do we practically implement this? So again, like we need to the actual phase shift because of the gradients is that this we can represent by this equation. Here we can say that this gamma is the aromatic ratio, and g of u is the strength of the gradient at time u, and x of u is the position of spin at time u. So we have two terminologies here. One is the zeroth order moment, which is applicable for the stationary spins. And the second one is the first order moment, which is applicable for the flowing spins. So so this is our gradient. This a little bit practically it is a bit different than the previous example. So what happens is that, like I change the polarity here. It starts from the negative lobe, then go to the positive lobe with higher amplitude and again come back to the negative lobe. So we can say that the first negative lobe is having minus G1 with duration of T1, and second lobe is having like amplitude of G2, positive G2 with time T2, and third lobe will be having minus G3 amplitude with time T3. So if we calculate the zeroth order moment, to just calculate all these things and integrate everything, so we usually get uh, 0. This is 0 here. So what happened to the first order moment? So first order moment, we need to actually calculate all three lobes because the t is actually changing because for stationary spins it is t, and for flowing spins it is t square. So what happens here? So you can, if you observe these three different lobes, first lobe, second lobe, and third lobe, you can see this integral part. First is 0 to t1, and it goes from t1 to t1 plus t2, and again like third lobe will be like t1 plus t2 plus T2 to T1, T2, T3. So again, if we calculate all these things, our criteria, the gradient design criteria should be in such a way that there should not be any net phase shift. So so after the integration, if we sum up all these gradient moments, finally we will end up getting 0. So that means we don't have any kind of phase shift if we apply flow compensation gradient along the flow direction. So one of the requirement for QSM is to acquire images with multiple TS. So how do we do that? So we can actually design the readout gradient so that the ADC can receive signals with multiple echo times, basically multiple Ts. So this is the simplified diagram showing only the RF and frequency encoding gradient portion. And we can see that each echo is stored as a separate K-space and separate K-space lines. So this is how the slice ordering looks like. So just usually, like for example, just assume that we have three T's, three echo times. So when we play the sequence, it will acquire all three echoes and saves us different K space. So the sequence actually will repeat again and again until all the K space lines are filled. So in an actual scenario, or the sequence actually will repeat approximately more than 100 times. It will repeat to fill the K space. So before going to the reconstruction, let's recap some of the very basic concepts. We know that the MR data is actually complex, meaning it has a real part and imaginary part. Usually, the images that we see and interpret are basically magnitude images, which are calculated from this complex data. So usually for normal MR imaging, we don't see these real and imaginary images. These are the real and imaginary images. In real world, like from the scanner view, we won't see these kind of images. But for QSM, we tap the recon. Basically, we set a display control variable so that it will generate these two type of images, which is real and imaginary. Then it will generate a magnitude also. So from this, it will calculate magnitude. So again, like this, typically the QSM consists of 5 echoes. So we get these 3 echoes from the scanner. So 5 into 3, it will be 15 images per slice position. And if we prescribe 100 slices, since it is a 3D sequence, the system will generate approximately 1,500 images. Yeah, so the data is pretty big actually. So we have this real and imaginary. Can we generate face image? Yes, we can. But there are some problems actually. So let me show that problem. So let me share my screen. So I'm actually sharing another window just in order to show the problem with the phase. So I'm going to load the real images first. This is I took like one slice from the QSM image. This is the real image. I just loaded this one real image, and I'm going to load the imaginary image also. So I just loaded the imaginary image. Let me calculate the complex. So I'm going to generate a face image from this. So this is how, so from the real and imaginary, if we generate a face by doing the complex math, we will end up getting this kind of images. See, we are getting like a lot of artifacts here, and this is called face wraps, or we can say face errors, and making this not usable actually. So this is a major problem while generating the face image. Let me go back to the presentation. So yeah, so here's the whole processing pipeline of the QSM. Scanner usually generate individual channel images because the coil we generally use is a multi-channel coil. The first step is to do a channel combination, and also like parallel imaging processing if acceleration is used. The next step is to the scanner will generate these three set of images per echo and per slice position. It will be like this is a real imaginary and magnitude images, and we will use these two images to generate our face image. Since face image has face artifacts or face wraps, we need to do the face unwrapping. So if after face unwrapping, the next step is, so we need to do the face unwrapping. So this is a face unwrapped image. After face unwrapping, next step is to do the field estimation. So uh, this is done using all echoes after removing the background field. We will pass this information uh, through an algorithm called a dipole inversion process to generate the final QSM image. The only purpose of this magnitude image is to create a brain mask, so that we can suppress the areas outside the brain. So this one. So let's see the all these individual processes how it works exactly. So let's see what is the problem with the face. So why is this wrap coming? We actually represent the phase from a minus pi to pi, or we can say that minus 180 degree to plus 180 degree. So if the phase change exceeds 180 degree, then it will wrap into this value, into a value where which is less than 180 degree. You can see this graph. In this graph, I have set up a phase value of 190 degree, but I am representing only minus 180 to plus 180, but my phase value is 190 degree, which means this is more than this representation. So what will happen? It will be assigned to minus 170 degree because uh, 360 degree circle, right? So what happens is that like 190 minus 360, it will be 170. So it will be, so this is our original phase. So it is plotted as minus 170 degree. So we can see that it is plotted as this actual phase, and it wrapped into minus 170 degree. Okay, if you still have confusions, let's see this clock analogy. In an analog clock, right? This is an analog clock. We have numbers from 1 to 12, right? So uh, how is 13 o'clock represented here? It is represented as 1 o'clock. So what is the problem here? The major problem here is that we don't know whether this is 13 o'clock or 1 o'clock. Basically, we don't know it is 1 a.m. or 1 p.m. The same thing actually happens with the phase. So how do we fix this issue? So there is a method called phase unwrapping. So what it does is that it will increase the range. So it will increase the range as it is here, we can see here, it is represented as minus 6 pi to 6 pi instead of minus pi to plus pi range. So the problem is that this is not that easy. This involves a lot of we need to solve a lot of mathematical problems. So one method to perform unwrapping is that to use a Laplacian method. So there are several methods available, but this is most common method, and let's see how this works. This method actually uses a Laplacian operator in order to detect these discontinuities, or we can say the jumps in the phase map. So then it will estimate the jumps or the discontinuities, and it will integrate these jumps into to unwrap the phase map. So here we can see that this is the wrapped phase, and we can see the 2D unwrapped phase. So what are the steps involved? First step is to compute the gradient of phase map. Then after that, we need to compute the Laplacian of the phase. Then third step is to integrate these two things to unwrap the phase. So yeah, so let's see how this works. First, we need to calculate the uh, gradient of the wrapped phase. So the gradient of the wrapped phase we can calculate by using this equation. So consider we have two pixels, for example, x and y. The phi of xy is the wrapped phase at position x and position y. So how do we calculate gradient? So we can get this gradient del phi. It is actually represented as del phi. This is actually the gradient. So we can get this gradient by taking the partial derivative of phi with respect to x and partial derivative of phi with respect to y. So if we do that, we will get the gradient in x and y direction. So the pixel information we can generate a gradient map. Next, so next is compute the Laplacian. Once we get the gradients at x and y, we can then calculate the Laplacian. So in our case, uh, the average value of phi around a point always differs from the actual value of phi because it is wrapped, right? So uh, it is always going to be different. So what Laplacian operation does is that it measures this rate so that we can say this delta phi of xy is actually the second order differential operator, which highlights the discontinuities, which is estimated by the Laplacian. So we can estimate these jumps because it is a second order. If we take the second order differential operator. So once we get the Laplacian and gradient map, we can integrate these things to actually unwrap the phase. So ultimately what happens is that if you use this particular equation, it removes the multiples of 2 pi, which actually caused the wrap artifact. Even though we remove wraps from our face, there are a lot of unwanted things outside the brain, right? See here, there are a lot of other unwanted things outside the brain. So how do we remove these? We can create a brain mask from the magnitude. So this mask is a binary, which means it contains only 1 and 0. So uh, uh, inside, we can say that inside the brain it is 1, outside the brain it is 0. It is very simple. So what happens if we multiply this brain mask with uh, unwrapped face? So what happens is that like wherever there is brain, it will multiply with 1 and remain same. And outside brain, it will multiply with 0 and it becomes 0. So ultimately what happens is that like we will get a final result something like this, the clean image. So wherever there is multiplied with 0, everything gone. And wherever it is multiplied with 1, it remains as it is. So this is a clean image we got after brain extraction. So this brain extraction, we can use several methods. So one is we can use FSL to estimate the bet. We can use SPM. There are several methods to do that. Python also we can use to generate this brain mask and do a simple multiplications to get this one. So we got a masked unwrapped face. Again, there are some issues. The image is actually a mix of internal tissue field and background tissue field, field. So the internal field is what we want, and background field is the one we don't want. This contains uh, several unwanted things like static field inhomogeneities, susceptibility difference between air and tissue, and some shim coil field. All these things will be there in the background field. We don't want all these things. We want to eliminate the entire background field from our actual image, and we want internal tissue field. So this is how it looks if we separate the internal and background field from this particular image. We are actually interested only in the internal tissue field and not in the background tissue field. So there are several algorithms available to remove the background field. I'm not going to details. You can refer these papers for all these things, how it is doing. So that's the tissue field map represented in hertz. So now we got a tissue field map and we remove the background field. Now this is a quantitative measure and we are getting the values in hertz. Now we need to convert this tissue field map into susceptibility map. So we use a method called dipole inversion. Just before going to the dipole inversion, just a quick recap of the basics. We know what is susceptibility. Susceptibility can be either positive or negative, and if it is a negative, then we can call it as a diamagnetic, and if it is positive, we can call that as a paramagnetic or ferromagnetic. So what happens is that all these materials disturbs our uniform magnetic field, something like this. Again, this is just a graphical representation of the magnitude of magnetic dipole in the direction of V0. This is our from down to up is our magnetic field. And look at this angle. This is very important actually. This angle is called magic angle. We like 54.7 degree. We all are like very familiar with called magic angle, which always create T2 prolongation appears, especially when we do the musculoskeletal imaging, it appears bright in T2. With the PD weighted image, if we use less than 30, 35 millisecond Ts. So the values here we need to concentrate here is that values along the magic angle is actually 0. So if these dashed lines, this is actually 0. And we can see that there are lobes of positive and negative field strength, which appears hyper and hyperintense in this graphical representation. We can simply call this as a dipole. And this is just an example how the dipole manifests in the filtered phase image of the SWA coronal reformat. Our intention is to remove the dipole effect so that we can estimate the quantitatively estimate the susceptibility variation. So how do we remove the dipole effect? So it is possible to create a dipole kernel using softwares. So there are like several software packages. If you are using Python, we have like modules to estimate kernels, dipole kernels. It is basically an array of numbers. So this is the graphical representation of the dipole kernel. in all three planes, axial, coronal, and sagittal. So now we have a dipole kernel. If we deconvolve each pixel of our tissue field map with this particular dipole kernel, we can eliminate the dipole effect. Okay, so how do we do that? The easiest approach is to go back to K-space. We have a tissue field map, right? Just do a Fourier transform. We will go back to the K-space. So in K-space, convolution becomes multiplication and deconvolution becomes division in K-space. So it is very easy to do the division rather than convolution in image space, deconvolution in image space. So we go back to K-space, we'll do divison, use this kernel and divide this kernel. Sorry. Hello. Yeah, divide this kernel by simply divide this kernel in the K-space. So after the division, what we can do is that like we can again do the inverse Fourier transform to generate an image, and this image will be our final QSM image. So there is some problem actually. Like if you see this particular image, this dashed lines, right? This area is actually 0. So that is a problem in our case actually. So what happens is that like if you do division and the zeros comes, we cannot divide by 0. So that will create a lot of issues while we do dipole inversion. So there are several methods to overcome this issue, and this is a major problem while doing the dipole inversion method or doing the deconvolution. One method is to use truncated K-space division TKD, so that actually do some processing to remove those zeros. Also, we can do like multiple angulations, so that if we angulate this 0 will we'll get 1 times 0, and if we angulate this one, we won't get 0. We'll get some values, right? So we'll estimate that value and do the math there, dipole inversion. But that is not a practical scenario. We need to we need to ask the patient or a volunteer to tilt our head and acquire data. That is very impractical to do that. So the other method, truncated K-space division, TKD kind of approach is preferred. This is one example, like I got it from Hackey's book. This is one example, like before deconvolution, how it appears. We can clearly see that dipole effect, bright and dark appearance in the vein. And after deconvolution, it is completely gone. We can say that the dipole effect is completely deconvolved. We can say this is again, it's a paramagnetic. Vein means like it's a paramagnetic, and we can confidently say that this is anything which appears bright on QSM is, we can say it is blood product. So that's all for now. Thank you for your attention. So this is like we are from 2015-16 batch, and yeah. So my colleagues are like Praveen and Tindu. Like Praveen is now in Siemens, and Tindu is now in UK. Yeah. With that, thank you for your attention.
Thank you, Sajith, for this extensive presentation. Now the session is open for discussion.
Sajith, I am Dr.